Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper from the Hugging Face trending list, published on November 24th, 2025, about 2 weeks ago. It shows that a new framework called ThreadWeaver can match strong sequential reasoning models, reaching 71.9% average accuracy and 79.9% on AIME24, while delivering up to 1.53 times speedup in token latency. The paper is titled ThreadWeaver, Adaptive Threading for Efficient Parallel Reasoning in Language Models. And as we will see later, the implications for faster reasoning without accuracy loss are pretty significant. Figure 1 illustrates how adaptive threading turns one long reasoning chain into several shorter, parallel ones so the model reaches the same answer with less waiting time. The top left panel shows traditional sequential reasoning that must finish each step before starting the next. The lower left panel shows ThreadWeaver splitting the math task into concurrent threads that later join. On the right, the AIME24 and Math 500 histograms show many problems enjoying more than 10% speedup without accuracy loss. Figure 2 shows a concrete example of how a single math solution gets split into coordinated parallel threads. The top of the figure presents the user prompt and the model's initial think segment, which lays out the distance formula. In the middle outline block, the model lists two subtasks, which describe what each future thread should compute. Below that, the thread lines carry out those subtasks independently in parallel, one for the horizontal difference and one for the vertical difference. The final sequential lines then combine both thread results to produce the boxed square root answer. Figure 3 explains how the orchestrator actually runs those parallel threads over time. The left panel shows the full reasoning trajectory text, with the prompt, the think segment, the outlines, the two thread snippets, and the final conclusion all laid out in order. On the right, the colored bars depict 3 time steps, where time step 1 generates the prefix and outlines, time step 2 launches each thread in parallel, and time step 3 resumes a single sequential stream. This schedule matters because it turns one long interaction with the model into several shorter calls that line up in parallel, cutting the total waiting time without changing the reasoning steps. Figure 4 explains how the training data is reshaped so the model learns exactly the same fork-join behavior used at inference time. On the left, the figure extracts all context and completion chunks from a worked math solution, marking only the generated pieces for loss. The middle strip converts these chunks into nodes of a prefix tree, which is a branching structure that shares common prefixes across paths. On the right, the tree is flattened back into one long sequence, while an attention mask forces each token to look only at its ancestors, so threads stay isolated but still reuse shared prefixes. Table 1 makes the central claim very concrete. Parallel threading keeps essentially the same math accuracy while shortening the reasoning chains. The top block lists accuracies, where both models stay around 72% on average, with tiny differences per benchmark. The middle block reports token latency, which consistently drops, for example, from about 10,000 to 7,000 tokens on Minerva Math. The shaded bottom rows convert those drops into speedups, showing average gains around 1.2 times and peak gains above 3.5 times on the most decomposable tasks. Table 2 shows that the ThreadWeaver model delivers both higher accuracy and stronger parallel usage than previous adaptive methods on AIME24. Self-parallelism speedup here means how many times shorter the effective reasoning path becomes when threads run concurrently. Activation ratio means what percentage of problems actually trigger parallel threads. The upper block lists multiverse and parallel R1 variants, which either parallelize weakly or suffer big accuracy drops. The bold bottom row shows ThreadWeaver, which combines the best speedup with roughly 80% accuracy, beating all other entries despite using a smaller base model. Wrapping up, the key idea is that adaptive threading lets one model split its own reasoning into parallel strands, keeping basically the same math accuracy while cutting token latency by up to about 1.5 times. This points toward faster, more interactive reasoning systems without custom infrastructure. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.